Welcome back, kids. In today's video lecture, we will discuss about spherical coordinates. In the last video lecture, we have seen about cylindrical coordinate system. We have also seen how to convert between cylindrical and Cartesian coordinate systems. In this video lecture, I hope by the end of this video lecture, you will be able to convert from spherical coordinates to rectangular coordinates given a point in the space. I will start with the basic spherical coordinate system and later on move on to the equations which relate the Cartesian coordinate system and the rectangular coordinate system. Before going any further, let us have a quick look about the spherical coordinate system. As discussed in the class, unlike a cylinder which will be having a base in the form of a circle, whereas the vertical dimension or the other dimension will be just like a longitudinal one, just like a height, what we call it as. So for a cylinder, we consider r, phi. The other dimension, this is just like a circle. The other dimension is a longitudinal one basically. So we will represent it as z basically. Whereas for Cartesian system, all the three dimensions will be in longitudinal, right? So you will be measuring them in x, y, z coordinate system. But whereas for a cylindrical system, two dimensions will be in the form of a circle. The third one will be just like your longitudinal one. Whereas for a spherical system, there is no particular thing called as a longitudinal one. So we will consider all these things in whatever the shape which you see. It will be just like looking like a circle. So that's why a spherical coordinate system, you will be having a radius, because in a spherical coordinate system, if you carefully see in this three-dimensional one, the center is somewhere in the middle, unlike a cylinder where the center we consider at the bottom of the cylinder. Here if you carefully see, this is your center. Now I'll consider this is r, in this direction also it is r, in this direction it is also r. So in all the directions we consider it as r, whereas for a cylinder in horizontal direction we'll be considering it as r, and other direction we'll consider it as z. But here in spherical coordinate system, it is just only r in any direction. So to differentiate from the cylindrical system, I will represent it as capital R throughout this course. So capital R represents the coordinates in spherical system, whereas a small r is generally used to represent in cylindrical system in this course. So capital R, and you do have this phi again. So similar to your cylindrical system, I do have r and phi, but the only difference is that instead of small r, I am representing it as capital R, and additionally you are having one more thing, what I call it as theta. Okay, so I do have now three coordinates, r, phi and theta. This r and phi are those coordinates which we generally employed in cylindrical coordinate system. Now additionally, I am employing this theta. 1 minute. So this is not phi, this is theta, which is the angle formed by the positive z-axis and line segments. So now three coordinates are theta and phi. Now the relation, see, this is r in all the directions. Let us suppose if I do have a small, if I decrease the r, then it will be just like this. So this is r and this is theta and this is phi representation. So if I do have a larger phi, then I will be considering a large amount of cylinder. If I do have a smaller phi, then my cylinder like this. So r, this is phi and this is theta. R, this is phi, this is, these both we have seen in the last cylinder things also. Additionally, what I am getting is theta. But here, what I will be using from this video lecture, I will be using, see, x, y, z for Cartesian systems, r, phi, Z for cylindrical systems. Here R I will represent as capital R, phi I will write here, additional angle is theta. This is cylindrical coordinate systems. Sorry, this is cylindrical coordinate systems. This is spherical coordinate systems. And this is rectangular coordinate systems. This is the representation which you'll be following in this course now, from now onwards. Now, as already been discussed, what are the minimum maximum values of R? It will vary from 0 to infinity, whereas phi vary from 0 to 2 pi, whereas theta, if you carefully see, the maximum value of theta will be at max, it can just be just like a flat line, right? So the maximum angle which you can get is 180 degrees. So that's why for theta, the maximum value is 0 to phi only. Whereas for phi, these two, I'll represent it as capital R from now onwards. Capital R and phi, those are similar to the cylindrical system, 0 to infinity, 0 to 2 phi. Additional theta, it will be from 0 to phi. Moving ahead, how to convert between spherical to Cartesian coordinates. Now let us suppose if a point has been given for you, P. Now how to convert that one into rectangular coordinates. Now this is the formula. X is equal to R sin theta cos phi, Y is equal to R sin theta sin phi, Z is equal to R cos theta. And whereas from Cartesian to spherical systems, these is the formula. You should remember these formula. We'll try to employ them. And between spherical to cylindrical. And spherical to cylindrical, as already I said, these two are same, right? These two are very similar. Basically, there is a small difference. Here, this represents the radius only of the base, basically, whereas this one, it represents the radius of the entire sphere. So, these are very similar, but there is a relation between these two. The relation between these two is R is equal to capital R sin theta. And phi, it is the same, whatever the phi which you will be getting here, it will be the same. And where the Z will be R cos theta. So this is the relation between the cylindrical and spherical systems. Similarly, whenever you have been given cylindrical coordinates, you need to convert them into cylindrical coordinates. What I will be doing is capital R is equal to square of R square plus Z square. Phi remains the same, whereas theta, it is tan inverse of, once I compute capital R, I'll go with tan inverse of Z by R. Okay. So this is the simple formula which I'll be using. Now these are the example problems which you are supposed to go through. Now I have given you a cylindrical coordinate system. Now you should convert them into Cartesian and cylindrical coordinates. And these do represent only a point, not a vector. Try to remember this one. These are equations which are used to convert coordinates of a point. Conversion of coordinates of a point, not the vector coordinate. Okay. So this is capital R, this is theta, this is phi. So if I want to convert from spherical to rectangular, you know the formula which I have already given you. You substitute them, you will be getting these things: 2, 2 root 3 and 4. Similarly for cylindrical, you know the formula R, phi and Z. You are supposed to compute the things. And similarly, finally, now I have given you rectangular coordinate systems. Convert them into cylindrical and also to spherical. Okay. Now, having said these things, now so far we have seen only about conversion between coordinates of points. Now, if I want to convert the components of vector, now let us suppose if I do have a component, a vector in the form of ax, x bar plus ay, y bar plus az, z bar. Now I want to convert this one into ar capital R bar plus a theta phi bar plus a phi, a phi bar. Now if I want to get the coordinates, Ax, Ay, Az are given for me. If I want to get them into Ar, A theta and Fi, now this is the formula which I'll be using. These equations are basically used for conversion of vector components, basically from one coordinate system to other coordinate system. Okay. Now, finally, differential elements. As already been said, differential elements. Now I do have, for a sphere, I do have 3 dimensions. One is capital R, the other one is theta, the other one is phi. So differential element in this direction in radius, because R will be moving in all directions, right? So if I want to consider only a small length R, so dr, and the direction will be R bar itself. Whereas for theta, it will be R d theta with theta bar. Whereas for phi, it will be R sin theta d phi into phi bar. So these are the differential terms: dr into r bar, r into d theta into theta bar, r sin theta d phi into phi bar. These are the differential lengths in various directions. Now if I want to add these three, see, this is the differential length in all the 3 directions. Now if I want to have only in one particular direction, I should use individual elements. Now these are all single dimensional elements. Now if I want to use a differential area, now differential area, I should use 2 components. So if I use R component, differential area, if I use R component, differential area, so it is having 2 dimensions. So if R is fixed, then theta will be varying and phi will be varying. So I should write it as R d theta and R sin phi d phi. So which means I'll join it. It is R square, sorry, this is sin theta, right? R square sin theta d theta d phi. See, R square sin theta d theta d phi. Similarly, if I want to have a surface area in theta, so it remains constant, the other 2 will be varying. So it will be R sin theta d phi into dr. This is for theta. So this is theta, R sin theta d phi into dr. So like this for other one also. And when I want a differential volume, because I want to consider a chunk of this entire sphere, so I should consider all these things. One is dr, the other one is R d theta, the other one is R sin theta d phi. So if I join all these things, R square sin theta dr d theta d phi. So let us suppose, what is the significance of these differential volumes? Now let us see if I want to determine the volume of sphere. Determine the volume of sphere, where R varies from 0 to 4, theta varies from 0 to pi by 2, and phi varies from 0 to pi. Let us suppose this is a sphere where the radius will be from 0 to 4, the theta value will be from 0 to pi by 2, and phi value will be varying from 0 to pi. Now if this is the case, then automatically how to determine the volume of a sphere for this particular case? So immediately what I will be doing, I will be utilizing this volume equation. See, I do have this volume equation, right? So I want to determine the volume. So I will consider volume means 3 things are there. In 3 dimensions I should find out volume, right? So R volume, phi will be varying, theta will be varying, right? So differential volume. So what is the formula of dV? So I will consider V is equal to R varies from 0 to 4 and theta varies from 0 to pi and phi varies from 0 to, sorry, theta varies from 0 to pi by 2, this varies from 0 to pi, and this is R square sin theta d theta and d phi. Now you know how to do these things, right? Triple integrals. First we will do with phi, next we will do with theta, next we will do with R. So this is the way how to find out the volume of a sphere or surface area or a differential lengths or lengths. So whatever the things, for determining this volume, areas and lengths, we do require this differential elements, and then we will integrate it. Okay. So I hope you do remember these formulas, and we will try to solve the problems in the next video lecture. So, but as of now, you just concentrate on converting between the coordinates, between the different coordinate systems, if point values are given for you. Okay. So this is one problem which you are supposed to do, and this is another problem. Solve this at home. And coming to the conclusion, yeah, the spherical coordinate system I'll be employing. So I'll change these things. This is r, theta, and phi. R, theta, and phi, and the maximum value of r is 0 to infinity, and theta it is 0 to phi only, and for phi it will be 0 to 2 phi. So this is our conclusion. Thank you once again. We will meet again in the class today. So I hope now you are able to convert from cylindrical to rectangular coordinate system and cylindrical coordinate systems, and also from spherical coordinates to other systems. Thank you all.